Hi. In this second presentation, we will discuss two main alternatives for representing finite state machines. At the end, I expect that you will be able to represent the behavior of finite state machines using state diagrams or algorithmic state machine charts, ASM charts, and to be able to convert them into equivalent VHDL descriptions. Accordingly, the presentation comprises these two main parts. Let's start by the representation aspects. You should be somewhat familiar with state diagrams by now, since I used this representation method to discuss the sequence detector. As it was said on that occasion, if we are designing a Moore machine, then the outputs depend solely on the state, and as such their value can be represented inside the state circle. It is shown in red in this slide. Moreover, and since there is only one external input in this case, we will only have two possible destinations as next state, according to whether the external input is 0 or 1. At each rising edge of the clock, the circuit will move to the next state and the output will be updated. Notice also that the state diagram will become significantly more complex as the number of external inputs increases, since it leads to an exponential growth in the number of possible next state destinations. The difference in terms of state diagram representation when we go from Moore to Mealy is that the outputs are no longer solely a function of the present state, and as such they can't be represented inside the state circle. Since the outputs are a function of the present state and of the external inputs, they will now be shown alongside the transitional arcs, which represent specific input combinations for each state. The best way to learn is to practice, and you should try to solve some exercises designing finite state machines in order to realize the challenges and to gain experience. The second representation method is the algorithmic state machine chart, or ASM chart. ASM charts take a lot more space than state diagrams, but are preferable for register transfer level designs involving operations that deal with multi-bit words instead of just single-bit signals. However, they can also be used to represent the behavior of finite state machines. The basic building block of an ASM chart is the ASM block. It represents one circuit state and comprises three types of elements: state boxes, shown as square corner rectangles located at the entrance of each ASM block and containing Moore assignments; decision boxes, shown as hexagons containing logic conditions and two output paths; and conditional output boxes, shown as round corner rectangles containing Mealy assignments. There is only one state box in each ASM block, which is always represented at the entrance of the block, and which will be empty if there are no Moore outputs to be asserted in that state. But there may be an arbitrary number of decision boxes and conditional output boxes inside the same ASM block. There is a direct equivalence between state diagrams and ASM charts, but the resulting visual representations will be quite different, because ASM blocks comprise a larger number of elements and therefore take up a lot more space than state circles. Yet, as the complexity increases, ASM charts may become preferable, particularly when involving more complex state transition rules. Let's now consider how to migrate from a state diagram or ASM chart into a VHDL representation. Take note of this principle. converting a state diagram or ASM chart into an equivalent VHDL description is a fairly simple and straightforward process. As we have said earlier, the difficult part of designing a finite state machine lies in converting the functional requirements into a formal state diagram or ASM chart representation. From there on, it's essentially a piece of cake. Once you have a state diagram or ASM chart, you can simply edit the VHDL design file of another project and update the port names and the next state or output sections. The next state section shown in this slide will have the same form regardless of being a Moore or Mealy machine, because in both cases we will move to the next state at the rising edge of the clock. As shown in this slide, we use case and if statements to consider the states and the conditions. There will be differences in the case of Moore and Mealy output sections, but actually any given finite state machine can have outputs of both types, so the best option is to include the templates for both sections in our file and just leave one of them empty whenever the corresponding type of outputs is not present. In this slide, we are looking at the outputs section for a Moore machine, which uses a case statement. The outputs are solely a function of the present state. In the case of Mealy machines, the output section comprises case statements enclosing if statements, the former handling the states and the latter handling the different input combinations. And that's it. As I said, what you need now is to practice. Thanks for your attention.